Pasha, what shall we do?
Yes, so we are on YouTube already.
Sorry?
We are on YouTube.
But can I become the host again? Because otherwise I cannot share. I can. Okay, all right. Can you see this, the heading of the lecture?
Yes.
All right, we start. Well, so the first section will be called the same way, almost holomorphic vector bundles. Oh. This will be a reminder of the subject, the definitions, the main definitions. The examples will come, I think, on the next lecture. Today we consider only the main general constructions, definitions, and facts. Okay, the first definition will be in terms of local trivialization. The first definition will be different. A holomorphic vector bundle is a triple. Say E, X, and Xi, where E and X are complex manifolds the first one is a total space of the bundle, and the second one is the base. And Xi is a holomorphic map, holomorphic surjective map. Sorry. So, okay. And the further properties are as follows. The requirements. First, that the requirement of local triviality. We can say Xi is locally trivial. Oh, the whole thing. Xi to X is locally trivial. I guess you know what it is, but I will mention it a bit later. And B is that for any point, say P and X, the fiber over it, which by definition is the preimage of X, is endowed with the structure of a vector space. In such a way that the operation of a vector space means that we can multiply with scalars, say complex numbers, and that we can add two elements. And both these operations should be holomorphic. Let us write this in the following form. The operation of multiplication with a scalar is a map from the product to E. And the operation of adding two elements from the same fiber. So I take the direct product, but I want to leave here only the pairs of elements from the same fiber, which is denoted by this way, in this way. I will decode this. Both these should be Halomorphic. Oops. Now the notation of the product over the base is by definition the following thing. It is one cross means product and the other cross means X. Is by definition the set of the following pairs. It's the subset in the direct product of the elements which satisfy that psi of X equals psi of Y, which means that the X and Y belong to the same fiber. And this is the operation of addition. And this is operation of the multiplication with the scalar, with the constant. Okay. Another equivalent definition uses the local triviality. Wait. The local triviality means A means that for any point there is a neighborhood where the bundle is trivial. No, sorry. In X, such that the restriction of the bundle to this neighborhood is holomorphically biholomorphic. To the direct product U times X, respecting the vector structure in the bundle, in the fibers. Compatible. This map should become linear in the fibers. Let me write it better this way. This arrow should be linear. This map should be linear in the fibers. Okay. Since the bundle is locally trivial, we can describe it in terms of local trivializations or charts and transition functions. So the second equivalent definition will be in terms of charts.
I'm sorry.
Yeah.
I believe there is a typo in the definition. First of all, the P should be in X, not in E, right? Any P.
Yes, thank you very much. Yes, you're absolutely right.
Yes, and also the preimage should be the preimage of U in the next line.
Yes, thank you. Thank you. Please always correct me.
And instead of X, after the arrow, there should be a vector space or something.
Yes, right. I'm sorry. Probably I'm not yet Okay, absolutely. Yes, and we should also write a holomorphic vector bundle over X of rank K. And this is K. This K places is called the rank of the bundle. It's the same for all points and their neighborhoods by definition, or you can easily prove it. All right, thank you. Another definition is as follows. I will formulate it in the following way. As a sort of proposition. Given a holomorphic vector bundle and using its local trivialization, I suppose that everybody has met sometimes such type of consideration, so therefore I'm very concise here. Using local triviality, one can pass to the following description. Open covering, choose the open covering such that the bundle is trivial over the elements of the covering. Of the base X. And transition functions. Where the transition functions are the following things. For the transition functions are defined on the double intersections if they are not empty. And the transition function is a matrix valued function, and for holomorphic bundles, it should be a holomorphic function. So it's a map from this double intersection to just to the complex Lie group, where K is the same K as above. When the transition functions come from holomorphic bundles, from a holomorphic bundle, first of all, they satisfy automatically the so-called one-K cycle property. Namely, that for on any triple intersection, we have that equals the unity in the group. And the transition functions are defined up to gauge transformations. And again, for holomorphic bundles, these should be holomorphic gauge transformations. So they are defined up to change. We can change the set of transition functions to the following thing. Where for each alpha, G alpha is a holomorphic map. Sorry. Is a holomorphic map from the open element of the covering Q alpha to the group. Again, it's a holomorphic matrix valued function. And now we say that any set of transition functions satisfying one cycle condition and define a holomorphic vector bundle, I mean the other way around. And those which differ by a gauge transformation define isomorphic bundles. So any set of matrix valued, holomorphic matrix valued functions, just in case, holomorphic matrix valued functions. Satisfying the cocycle condition defines a holomorphic vector bundle of rank K, and those transition functions which differ by a holomorphic gauge transformation. Those give the same vector bundle or isomorphic, as you wish. Halomorphic, of course. Again, okay. Now, if there are no questions of this type of definition, then I proceed. First, let me please ask anytime. Feel free to ask. By a smooth vector bundle, we understand approximately the same thing, just lifting the condition of holomorphicity. So smooth bundles are defined in the same way. Smooth or topological bundles, then in topology we require only continuity, that everything is continuous. But smooth and topological is very close. Anyway, smooth bundles are defined in the same way, except that we don't require everything to be holomorphic. That everything, no, sorry, except that, let me, there is no requirement of holomorphicity. This means, in particular, that over a complex manifold, say X, the bundles, the holomorphic vector bundles of rank K are a particular case, are a sort of, they are like smooth bundles with additional structure. Not particular case, but with additional structure, are actually, or can be considered as smooth bundles with fiber, with complex vector space fiber, with fiber CK, are endowed with an additional structure. What is this additional structure? A choice of such transition functions among inside the gauge equivalence class, such a choice that the transition functions are holomorphic. Yeah, I will not describe this. This is more or less clear, but this will be useful for me later. Additional structure. This gives us a point of view at a second equivalent definition. So let me mention, this is somehow like, let me mention that it is equivalent. Unfortunately, I formulated it rather as a lemma than definition, but I hope you will understand me. Now, actually another definition, which is again equivalent. No, let me start from an auxiliary definition. Given a smooth vector bundle, such that its base is a complex manifold, and now I want to define the notion of a D-bar connection in a smooth bundle. Everybody knows the notion of a connection in a bundle, and this is it's relative, which uses only Dalbo operator instead of the full DRAM. I will make a remark later that you will recall, you will see the similarity. At its base, a D-bar connection, smooth vector bundle, say E, connection in E is the following differential operator. Is a first order differential operator on sections, on smooth sections of E, or more precisely on differential forms with values in E. Let me just operator say nabla bar, which acts on 0Q forms on X with coefficients in E, and makes 0Q plus 1 forms. And satisfies the Leibniz rule. Namely, if does everybody clearly understand what means this symbol? 0Q forms with coefficients in a smooth bundle. These are smooth objects. This is an infinite dimensional space of globally defined 0Q forms times the bundle. Okay, if nobody asks a question, I suppose that it is clear. Then the Leibniz rule means the following. We can multiply elements from this space with 0Q forms, ordinary 0Q forms. And we have Dalbo operator on 0Q forms. So if we act with our operator of the connection, of D-bar connection, on such a product, say alpha, which we can write wedge or just dot or nothing here, but let me write in this way, where alpha is just a 0Q form. I put dot, just meaning arbitrary value. And S is element from this space. So if we act on such a product, it should be fulfill the following, that it's the same as acting first with the ordinary Dalbo operator, plus minus 1 to the degree of alpha, which nabla bar acting on S. Natural product, the natural Leibniz rule. Okay. And the final sentence in the definition is that nabla bar connection is called flat.
Сейчас, там опечатка, да, там к первому тоже применяется градиент.
Кому?
Алло.
No. The first guy is an ordinary 0Q form. So On zero pure forms, we have Dalbo operator, which was defined before us. Okay? And now using the understanding of what Dalbo operator is, we can define what nabla bar connection is. Okay?
Сейчас, мне что-то не понял. Альфа это обычная форма, а S это сечение уже расслоения, да? В этом разница.
Yes, right. Is called flat if it squares to zero. So reminder will be about the notion of the ordinary connection. An operator nabla. Okay, let me use another letter probably. Operator D from K forms with coefficient in the bundle to K plus 1 form. So here I mean just forms without separating them into PQ type. In particular, what I'm writing now applies also to the case when X is not a complex manifold and there are no notion of the zero Q forms. Satisfying the Leibniz rule of the following form. And here's the main difference, that on the first place, there is a de Rham differential, not Dalbo. And the rest is the same. This guy is called ordinary connection. We don't need this probably, but definitely not at the moment. But just again, remind that when X is complex, one can write any connection can be written as a sum of two parts. Where nabla bar is a D-bar connection, we don't need this actually. And nabla is a D without bar connection. And to make this more clear, let us consider this. This is just a notion of connection, okay. And also, it is important for us to understand what does it mean flat connection, flat D-bar connection. Okay. In the case of ordinary connection, I should have said, for an ordinary connection, as it was defined just above, its square is a zeroth order differential operator. So it's endomorphism of a bundle. Zeroth order differential operator. And it's called the curvature. Of the connection D. So in the D-bar connection, we could have defined the notion of the curvature. We don't need it, but we could have done this. But the requirement of flatness means vanishing of the curvatures in the case of ordinary connections. All right. Now the definition, an alternative definition of a holomorphic bundle. It is alternative and equivalent. It will appear now as a smooth bundle with additional structure, namely the D-bar connection. Okay, a holomorphic vector bundle over a complex manifold. X of rank K again is a smooth vector bundle of the same rank. A smooth vector bundle with complex fiber I need. So those are called just complex vector bundles. You should not confuse the words when somebody says complex vector bundle or holomorphic vector bundle. Complex means it's an object in topology. It's a smooth or topological bundle with complex fiber. A smooth complex vector bundle E. I don't need it actually. A smooth complex vector bundle of rank K, which means the fiber CK of rank K endowed with a flat D-bar connection. Remark, we shall now demonstrate that the two definitions are equivalent, but before doing this, let us look at what sections of holomorphic vector bundle mean. Okay, let E be a holomorphic bundle. A holomorphic map from the base to the total space in the opposite direction to the projection is called a section. I repeat, a holomorphic section. if for any definition of a section, if it is compatible in the following way with projection, if the composition of the projection psi and S equals identity on the base, which means that the image of the section intersects each fiber at one point. Exactly at one point. All right. Now let us see what is the definition of a holomorphic section in the case of the second way of defining a holomorphic vector bundle, in case of this definition. This was, I mean, what I started with, these words were formulated in terms of the first definition, right? So in terms of the second definition, holomorphic sections appear as a zero modes of the differential operator, the kernel of the differential operator. So I write it as follows: holomorphic sections are smooth sections which are annihilated by the operator nabla bar. Those which belong to the kernel of nabla bar. And this can be, and should be, considered both ways of understanding the holomorphic sections. Both, this should be considered as globally as also locally. So this applies to sections also to sections over open subsets. Okay, so let us discuss equivalence of two definitions in short. Let us do as follows. Suppose we are given a holomorphic vector bundle understood in the first definition. we can always choose such small. No, okay, wait. Maybe I change in the second definition. Sorry, I better try. Yes, I better start from the second definition, right? Sorry. Understood in the second definition. That is, we have a pair. A holomorphic bundle is a pair, a smooth bundle, and flat connection, flat D-bar connection. Okay, so then we can choose we can choose such a small covering, such a covering U alpha of X that each open set U alpha is sufficiently small in order that I'm choosing the bravest version of words, such that okay, such that one can find a trivialization over U alpha, over U alpha, again, such that nabla bar becomes just D bar. In other words, one can represent the nabla bar D bar connection as a pure gauge and use the holomorphic smooth gauge transformations. Let me make a remark here, probably. Let me first finish. Then one can see that the transition functions become, with this choice of trivializations, the transition functions become holomorphic. With the, when we change the trivialization, in particular, we choose it to fulfill this equality. The transition functions change, and with this particular choice, they become holomorphic. And therefore, we come to the first definition of a holomorphic bundle. So the exercise is to think about this. And find also the argument in the opposite direction, how to come from the first definition to the second. how to define a D-bar connection if you are given holomorphic transition functions. And remark is about the local shape of D-bar connection. Again, given a pair smooth bundle D-bar connection, which is flat, okay, not flat maybe yet, we can always find local trivialization in the smooth sense. We have local trivialization, local smooth trivialization. Where not such that, but in any smooth trivialization, the operator of connection can be written in terms of connection one forms. Where I do not explain this formally, hoping that everybody understands. So in local trivialization, as always, as for ordinary connection also, we write it in this way, where A bar is a 0-1 form. With values in our smooth bundle E, with coefficients, if you want. So reminder is that for ordinary connection, the same thing. Locally is written as the RAM operator D plus 1 form. Oh, sorry. Not with values in E, with values in matrices. And here, for ordinary connection, it's a 1 form. With values in matrices. Or Lie algebra, if for more elaborate versions. Okay. Now, flatness of a D-bar connection.
Можно вопрос спросить?
Yes.
А вот А-бар, оно... Извините, что я на русском. Вот А-бар, оно... Ну, то, что оно А-бар, это означает, что это какая-то там функция, умноженная на dz с чертой, ну, то есть на антиголоморфную часть. А сама функция, она голоморфная функция, ну, в смысле, она зависит, она может быть голоморфной, она может любой функцией быть, или только там антиголоморфной или голоморфной?
Вот эта буква, да?
Да, как она записывается как dz с чертой, умножить на что-то, да?
Yeah. The question was whether this 0-1 form is holomorphic or not. It cannot be holomorphic because for 0-1 form, there is no notion of holomorphicity. It would depend on coordinates, if you want. There is a notion of D-bar closeness, which we now shall mention. The same way as here, the connection does not have to be constant. But flatness means that it is satisfies zero curvature condition, right? Which in abelian cases that A is closed. You shall see, I was just about to write. The flatness means the following thing, that D bar applied to A bar plus A bar wedge A bar equals zero. Analogously to the zero curvature of the full connection, of the ordinary connection. So in abelian case, so which means for k equals to 1, we have just closed. The change of local trivialization is reflected in that connection, one form changes by a gauge transformation. I mean of a change of local smooth trivialization. It produces the following change, gauge transformation. Okay, let me put it here. G is a smooth matrix valued function. Okay. Did it become clear?
Ну да, вроде стало понятнее.
All right. Okay. Okay, and now let us introduce a notation. We shall denote by gamma of x, comma e, where is x a manifold, complex manifold, e is holomorphic bundle, the set of all holomorphic sections. Of a holomorphic vector bundle E. Over X, okay, over X. All right, now we pass to a second subsection, which will be called homology of there is a different there may be different uses of words, so we can say of or can say with coefficients in. Halomorphic vector bundle. I'm sorry for jumping screen, but somehow I cannot resist. Of holomorphic vector bundle. Okay. Let me also add to the previous item about notations. So the same notation for a smooth bundle. Smooth vector bundle. In principle, the same thing is defined. Gamma of x comma e means the space of all smooth sections. So in this sense, the nature of the space of section, which sections are taken, depends on the second letter. If it belongs to holomorphic category, then we speak about holomorphic sections. If it belongs to smooth category, we speak about smooth sections. Smooth sections of a smooth bundle E. Oop. Okay, anyway. So let me somehow separate them. Like this. Okay. What do you think of this way of making a lecture? In principle, we have time from 14 or 2:30 to 5 p.m. What if we take a 5 minutes break somewhere in the middle and then finish at 5 or 5?
To 5 or to 4? Because the lecture is hour and a half.
Yeah, wait. The end is, sorry, the end is supposed to be 4 p.m.
Yes.
So if you make a 5 minutes break each time, each lecture, then and finish 5 minutes later than scheduled. What do you think?
Я думаю, это здорово было бы. Перерыв небольшой, после этого лучше. Я лично лучше соображаю.
All right.
But
Okay,
today we
so
have only 20 minutes left. I'm not sure is it reasonable.
Sorry, say again.
We have only 20 or 25 minutes left. So
Yeah.
I'm not sure that it's reasonable to do a break now.
Okay.
Yeah, but if
other opinions, we have two opinions. One is in favor, one is against.
Ну, мое мнение скорее...
I'm in favor. So we have two in favor, two pro and one contra. If anybody says nothing, we make a break.
А можно я сейчас скажу? Просто я имел в виду скорее общую ситуацию, когда 20 минут, конечно, ну, типа надо перерыв делать где-то посередине лучше, конечно, там, типа, вот если у нас...
Of course, as a rule, we shall make a break in the middle, but this only came to my mind now, therefore I asked. Okay, anyway, 5 minutes break. And this will be each time unless somebody complains, all right? See you in 5 minutes. Okay, I think 5 minutes have passed. So, does somebody hear me? Say something, please.
Yeah.
Okay.
Yes,
All
we
right.
hear.
Thank you. So, given a holomorphic vector bundle in the shape of the second definition, we have a smooth bundle and an operator of d-bar connection. Then the operator squares to 0. And as soon as we have some operator which squares to 0, we can always think of cohomology, because it's the kernel belongs to the image belongs to the kernel. So in more detail, it is as follows. We have spaces of sections, 0 forms with values in E, in the smooth bundle. Smooth 0 forms, which means simply sections. It's the same as this guy. Then 1 forms, 0 1 forms. Oops. And so on. Q form, 0 Q forms, 0 Q plus 1 forms. And everywhere we have the operator, nabla bar. So on up to the dimension of the complex dimension of X. And to let me label these operators in their, let me label differently different components. This will be temporarily nabla 0, nabla 1, nabla 2, nabla Q, and so on. And what we write as a whole thing in components looks like this, that nabla bar with label Q plus 1 times nabla bar with label Q equals to 0. This is just the composition of operators. Therefore, it means the same thing as saying that the image of the operator nabla Q belongs to the kernel of nabla Q plus 1. Therefore, we can define the cohomology groups, which are the vector spaces, complex vector spaces. They're called groups for historical reasons. H, Q of X with coefficients in the, let me denote this way, in the holomorphic bundle E, straight E, Roman E, as the quotient space, kernel. Yes, I always make this mistake in lectures, not in life. Let me write in this way. The kernel of this guy, the quotient of this guy by its subspace, the image of the previous operator, nabla Q minus 1. Analogously to the RAM cohomology, right? Or Dalbo cohomology with trivial coefficients. Okay. Well, very good definition, but now we have also another way of considering a homology, namely what is called Czech homology. This is formulated in terms of open coverings. So this was, this was item, say, A. And B will be Czech homology. Czech. Now we shall define a complex of vector spaces, which is constructed from the holomorphic bundle, where we shall use probably more the first type of the definition. But anyways, we only need the notion of a local holomorphic section. So is complex of vector spaces let them denote by C, Q, which are constructed from the holomorphic bundle E. So let me start from the zero. These are called spaces of K-chains. Czech. Czech Q K-chains. So the space seabird Q of first, let me define the zero K-chains. Wait, I forgot the covering. The Czech complex is defined with respect to a covering. I should have started from it, but now let me somehow repair the situation. These guys are constructed from an open covering U alpha of X and a holomorphic vector bundle E. So now we are given some covering, which in principle I should have reflected somehow in the notation of the complex, but I do not mention covering, understanding that I take some covering, fix it, and obtain some complex. Then I will mention how the whole thing depends on the covering later. So the space of zero K-chains C bird not of E is the direct sum over the elements of the covering of the spaces of holomorphic sections of the bundle E over each open set. Again, holomorphic sections, just reminding you, over U alpha. So local holomorphic sections. One K-chains is very similar, but we take double intersections. Such that U alpha beta is not empty, and take gamma over this intersection. So sections on open sets which are intersections, and so on. Q chains, C Q of E is direct sum of indices U alpha gamma Q. How to say, tuple intersection. And we take holomorphic sections there. Of course, in practice, when the dimension of the manifold is some fixed fine number, we don't need intersections of very high order. One can always choose a covering where which ends, I mean, how to say, if the complex dimension of X is n, and the real is 2n, we can use coverings where there are at most two n intersections. Wait. There are at most, There are at most 2n plus 1 intersections. If you understand this, the how to say, кратность пересечения. Did you understand me? Intersections. I mean, double, triple, and so on. At most 2n plus 1 to intersections. Okay, now we want to define the differential in this to make it a complex. So the Czech differential. Let us denote it by, say, again, I first denoted component-wise, but then I forget this index. It maps Q chains to Q plus 1 chains. And first, let us start from 0 chains. So a zero chain is a set phi alpha, where alpha is the same label as the label of the covering, and I should get something labeled with 2 labels, okay, by the following formula. For Next step, what if I act with a differential on one k-chains? I should get to the space of two k-chains. One k-chains are sections on each double covering, phi alpha beta. And they get sections, local sections labeled by 3 labels by the following formula. My notation is such that when I label, say, phi, not say, just, okay, for example, for one k-chains, I label them by 2 indices, and the open covering intersections, double intersections of the elements of the covering are labeled by 2 indices, and we have that U alpha beta and U beta alpha are the same. But the k-chains I will label antisymmetrically, so it will be like this, okay? And antisymmetric in general. This is just for convenience. Okay. Now, exercise. Find the shape of delta Q, for example, in textbooks, and check that it is a differential in a complex. In the case of we considered, it is clear that delta 1 composition delta naught equals 0. If we compare delta naught and delta 1, obviously the composition is 0.
Можно спросить, вот условие, ну то, что вот когда мы про расслоение говорим, мы говорим, что там условие 1 к-цикла, это как раз вот к-цикла вот в этом смысле, только надо сложение на умножение заменить.
Absolutely. I was about to make this remark right now. Consider a rank 1 vector bundle. With transition functions, or defined in terms of transition functions, or vice versa. Anyway, with transition functions, G alpha beta, we have a set labeled by 2 indices. And the following applies to both to smooth or holomorphic case. So the one cocycle condition mentioned above namely G alpha beta, G beta gamma, G gamma alpha equals 1. If we pass to the logarithm, will become the Czech additive Czech chain cocycle condition. So if we can express G alpha beta as an exponential of a phi alpha beta, then the latter will satisfy equals what?
0.
No, 2p I say k. So in this way, given a multiplicative cocycle, we don't give an additive one, only up to integer numbers. And this will be important for us in some later lecture. But in opposite direction, the same way.
Sorry, but these phi are not the same phi as was defined above, yes? Because
above there was no phi defined.
Yeah, that was you.
It was just used, okay? There was no particular choice of phi. If you mean here.
But their meaning is different, yes?
Sorry, say again.
But their meaning are different because
in a sense, but in particular case they are the same.
Because
let me write. This is similar to Czech differential if we take the trivial bundle, if E Halomorphic bundle or smooth bundle. As I said, this applies to both situations of a smooth bundle or Halomorphic bundle. So if we take the coefficients in the bundle, which is trivial, the trivial rank 1 bundle. Okay, now our time elapsed. So we finish here and we start. This will, I will discuss more details on this point actually, but in a more abstract formulation, which is much more convenient. So let us remember this observation that additive cocycles modular integrals is the same as multiplicative abelian multiplicative cocycle. Wait, I should mention just last remark. There is a non-abelian version of the one cocycle, which we know, which means description of vector bundles of arbitrary rank, but there is no non-abelian analog for high differentials, high Czech differentials. There is no non-abelian multiplicative, just to stress. analog of Czech differential. Hurry. Czech chains and differentials. And differentials. For Q greater than 1, then 2. Greater than 1, yeah. Strictly greater than 1. For Q greater than 1. Okay, thank you very much. Any more questions?
Сейчас вот можно такой вопрос про 2 пи Ну, то есть все-таки ну, то есть как бы оно все-таки немножко портит то, что это как бы ход циклов.
What is written above in a frame means the following. That we need a little bit more definitions to write this. We consider Czech. Oh, sorry. Probably I was. Wait. Give me a second. Okay, let me write. But actually, it refers to a further discussion. But since you are interested, let me write as follows. Just a second. I will introduce additional notation, but very clear and short. In order to write this, that there is a one-to-one correspondence between two types of Czech cocycles. So Czech cocycles, actually, and homology also, but I will mention later. Cocycles are with coefficients in it will be what I'm going to write now will look at as a tautology actually, but it's sort of useful tautology. First, we considered Czech cocycles with coefficients in sections of some bundle, smooth or holomorphic. We considered holomorphic case, but they could be smooth also. They are not interesting in the case of smooth sections, as will be mentioned later. But in case of holomorphic sections, they are interesting. So we can write this. Wait, let me write for smooth. It will be not exactly what we discussed in the holomorphic case, but it's smooth analog. So Czech cocycles with coefficients in smooth non-vanishing functions. Is it clear what I mean by Czech chains and cocycles with coefficients and such things? It's the same as sections, but functions, simply or sections of trivial bundle. But I want to think of them as of functions and require that they nowhere vanish. Okay. And Czech cocycles with coefficients in smooth functions. Let me see. No, but okay, I'm sorry, and I wasn't prepared to this question now. I better tell you about this later, okay? I was planning to mention this, but it will be more clear. Now, otherwise I would spend like 30 minutes now because I simply don't have notation, all right?
Окей.
Can you forgive me for this?
Thank you.
Okay, I don't
Душа,
forget.
спасибо.
We come to this stage here.
Мгм.
Okay, sorry. It will be too long, I did not realize. Any more questions or everybody left? Okay, so if no more questions, then I stop recording. And say goodbye.
Спасибо. До свидания.
Thank you. Спасибо.
Thank
До
you.
свидания.
Goodbye.
Thank you. Goodbye.